This is part 2 of rational functions. We're going to start with a pretty quick review, but a pretty thorough review of what we saw in part 1, and then we're going to quickly move into putting all of the pieces together. So a rational function is a fraction. Let's go ahead and start off with an example. Let me grab my pen. Okay, and then we'll make this so you all can see. So just reviewing some tools here. I want to start off with an example. So let's say that we've got f of x is equal to x squared plus 2x plus 1 divided by x squared, let's do minus 1. I'm going to factor this one, x plus 1, just anticipating what we need to do next. And then x plus 1, x minus 1. We're going to go ahead and start with the domain. So domain restrictions. So domain is, we need to throw out 1 and negative 1. We were writing those as intervals, so you can write that as the interval negative infinity 2. I can go up to negative 1. Union, negative 1 to 1, union 1 to infinity. What's important though here in terms of the rational function is that I can cancel this one. That tells me that I have a whole at negative 1. Let's put the arrow there. So I've got a whole at negative 1. The x minus 1 does not cancel. It should be negative 1. The x minus 1 does not cancel. So that means that we've got a vertical asymptote at x equals 1. So if it cancels, we have, I'm going to make this so it's a little easier to read. So if it cancels, we have ourselves a whole. If it doesn't cancel, there you go. If it doesn't cancel, that means we've got a vertical asymptote. So we already have things set up for our function. I can go ahead and just start graphing here. I really can't put the whole in yet, but I can go ahead and put in that vertical asymptote at 1. So we've got that boundary there at x equal 1. And I'm just going to make myself a little note that we have a whole at negative 1. The second piece that we did in the other video was to look at horizontal, so a horizontal or a slant asymptote. And this comes from end behavior. When I'm looking at the end behavior, I notice that I've got equal degrees. So I've got the degree of the numerator equals the degree of the denominator. That means that I can go ahead and just focus on those two lead terms. And I really just want what that simplifies to. So y approaches x squared over x squared, which reduces to be 1. So I have a horizontal asymptote at y equals 1. I can draw that in here. Y equals 1. And I'm going to let the calculator, at least for now, since we're reviewing, do the rest of the work. And then I want to do a couple more examples with the horizontal asymptotes. We just haven't done many of those yet. Let's go ahead and put this one in, and I'm going to put it in its not factored form. That way I can also verify my factorization was correct. So x squared plus 2x plus 1 over x squared minus 1. Okay, let's take a look. Let's change this from black also. Go to settings, and I'm just going to choose a nicer color like blue. Give myself a little bit of a different viewing window here, and I can see that it looks like I do have a vertical asymptote there at 1. If I evaluate my function at 1, it should be undefined, and it is. With that horizontal asymptote, I can actually type it in. So it looks like my y values are approaching 1. Do you see those y values go from 0.89 to 0.9? So I can also type in here y equals 1. Nice thing about these, see, I'm highlighted here. Let's go ahead and go to settings. I'm going to change the color to orange and we'll do dotted since it's just a boundary. And it does make a really nice boundary, so I can see that I've got the right idea there. Okay, so thank you, Desmos. Let's take a look at just a few more examples here. So I'm just going to draw a line and then we'll do a few more examples with the horizontal or slant asymptotes. Horizontal or slant. So here's our first example. Let's say that we've got f of x is equal to 6x cubed minus 2x plus 1 over 3x cubed minus x. I notice that my degrees are equal, like we had in the last one. Since the degrees are equal, I just look at those lead terms. Y is approaching 6x cubed over 3x cubed. The x cubes cancel, and I can go ahead and reduce. And this gives me a horizontal asymptote at y equals 2. Okay, let's do another example. Number 2. For number 2, let's go ahead and say that our function looks like this. Let's say that we've got 3x squared minus x plus 1 over 2x to the 5th minus x squared minus 7. For this one, my degrees are not the same. My denominator's degree is bigger. So the degree of the denominator is bigger than the degree of the numerator. This tells me that my horizontal asymptote, these are nice because I don't need to do much else, is at y equals 0. The other type that we saw would look something like this, number 3. Let's say that we have, let's do x squared plus 3x plus 3 divided by, oops, I meant 3 there, divided by x plus 2. So for this one, let me fix it. There we go. So for this one, I see that my degrees don't match, but this time the degree of the numerator is bigger than, that's supposed to say degree of the denominator. So we have a slant asymptote. And I need to do just a little bit of long division. Do you think I can write it that tiny? I'm going to try. I can actually make this bigger. I'm going to try. So let's do x plus 2 into x squared plus 3x plus 3. The nice thing is I don't need the remainder. X into x squared goes x times. That's going to give me x squared plus 2x. Let's subtract. That goes away. I get 1x plus 3. X goes into x 1 time plus 1. That's really all I needed. This is my slant asymptote right here. So my slant asymptote is at y equals, it's that quotient x plus 1. Okay, so there's our overview. Let's go ahead and put it all together with some examples. So for the first example, I'm going to go ahead and just make it up. And let's say that we've got, I'm going to put it in factored form, f of x is equal to x plus 2, x plus 3, all divided by x plus 2, x minus 5. The domain is all based on the denominator equal to 0. So denominator can't be equal to 0. My domain here, let's see, so this would be x plus 2, so x can't be negative 2, and x cannot be a 5. Negative 2 comes first, so as an interval, negative infinity to negative 2, skip over that, negative 2 to 5, skip over 5, 5 to infinity. Phew. Could also do that in set builder notation. All the x is such that x is not a negative 2 or a 5. Okay, holes. Holes are based on the domain restrictions that cancel. So these are going to be the factors that cancel. We have two domain restrictions. These can be either a whole or it can be a vertical asymptote. But -2 comes from a factor that cancels. So this tells me that I've got one whole, and that whole is at x equals -2. Okay, vertical asymptotes. The 5 then, because we've already taken care of the -2, the 5 has got to be a vertical asymptote. So these stay. So these are the factors in the denominator that stay. Well, this x minus 5 stays, which means that its domain restriction of 5 is a vertical asymptote. So we're going to write that as x equals 5. We go ahead and just put a little yellow square around each of my answers here. Okay, there we go. Now we're going to move on into horizontal asymptotes. For horizontal asymptotes, it's actually really helpful to have this guy multiplied out. So I'm going to write it multiplied out, and I'll do that in green. Just doing a little FOIL here. So this is going to be x squared plus 5x plus 6. In the denominator, we get x squared minus 5 plus 2, so minus 3x minus 10. It's based on end behavior. So I'll write it in green. So it's based on end behavior. Another really good way of saying that is it's based on the degree of numerator and denominator. Take a look at that in factored form. You can see that they have the same degree, which means that my horizontal asymptote is just the coefficient out in front. X squared over x squared tells me that y goes to 1. So my horizontal asymptote is y equals 1. There's no slant asymptote. It's either one or the other. So if there's a horizontal, that means there's no slant. I'll put that in parentheses here. Okay, so now for the intercepts. To get an x-intercept, I need y to equal 0. My function is this guy right here. I could set this entire fraction equal to 0, but I know the denominator is never going to equal 0. It would be undefined. So I'm really only going to get an intercept if the numerator is equal to 0. So I'm going to go ahead and take my function, and I'm going to simplify it as I go, though. So watch what I do. This is plus 3. And then in our denominator, I'm going to write it all out, x plus 2, x minus 5, x minus 5. These cancel, and that's important. So we get 0 equals x plus 3 over x minus 5. I'm going to cross multiply. 0 times x minus 5 is 0. So 0 equals x plus 3. So our x-intercept is at x equals -3. So x equals -3. As a point, I put these together. -3, 0. Whoops. No, you can't help me. Okay, let's just let that guy go away. There we go. Okay, nice little break there. Stop. There we go. So where was I? Based on y equals 0. So we've got the answer here for this one. It's that point. For the y-intercept, we've done these. To get a y-intercept, we're just going to let x be 0. So we're going to let x equal 0. I think the easiest place to do it is with the form that's multiplied out. It really doesn't matter, though. So if I let, I'm just going to do it up here. So if I let x be 0, I get 0 plus 2 over 0 plus 3 over 0 plus 2. That cancels anyway. You can just get rid of that. 0 minus 5. So I get 3 over -5. So my y-intercept is -3/5. Or as a point, 0 for x, -3/5 for y. How could you check these? It's a lot of work. We have not even looked at the graph. I would actually probably start with the graph instead of getting all of my answers first, but I didn't. So let's go ahead and take a look at the graph here. My graph, I'm going to put it, since it was given to me in factored form, I'm actually going to do this guy in factored form just because I think it's going to be a little bit better in terms of checking it. There we go. Okay, so f of x is equal to, give myself a rational function here, x plus 2, x plus 3. You could certainly do the other form, x plus 2, x minus 5. It's also a great idea to type in your horizontal asymptote. That was y equals 1. Let's make sure that we had that right. Y equals 1. And I'm going to make this dotted. Okay, let's take a look. Okay, so here it is. That asymptote looks great. Let's also take a look at our intercepts. Okay, so here they are at -3 and -0.6. So -0.6, is that -3 divided by 5? And yes, it is. So I'll just let that one be checked. What I can't put in here is the vertical asymptote, but it certainly looks like it's at 5. 5 would be right here in the middle. And I can make sure that this is a domain restriction anyway by typing in y equals 5, and it is. So we were able to check the horizontal asymptote, the intercepts, so here they are, -3 and -0.6, and then we can at least sort of verify what our vertical asymptote was. Okay, so that's our process. Let's do another example. And let's go ahead and start by graphing this one. Graphing, I think, is a great place to start. This one is given to us not in factored form, so I'm just going to go ahead and type it in its original form, equals, and then I want, there it is, 2x squared minus 10x minus 28 divided by x squared plus 3x plus 2. As I take a look at this, it looks like I have a horizontal asymptote, and I can see that I've got an intercept of 7 and an intercept of -14. So Desmos does quite a bit of the work for us, which is really, really nice, right? Let's put this in factored form and work through some of the algebra here. I'm going to be in blue. I'm just going to factor this guy. And factoring helps me with a lot of things. So f of x is equal to, let me make this just a little bit smaller as well, equal to, let's see, I can pull a 2 out of that numerator. So x squared minus 5x minus 14. And I'll factor that one even further. And this becomes x plus 2x plus 1. Okay, so 2, x, 7 and 2, right? So minus 7, x plus 2. And then x plus 2, x plus 1. I do have a hole. These cancel. So we have a hole at x equals -2. This one doesn't cancel. So I have a vertical asymptote at x equals -1. So my domain, I've got 2 of them, right? So -infinity, I come up to -2 first. Union, -2 to -1, union, -1 to infinity. Holes, that's the one that canceled. So that would be at x equals -2, comes from the one that cancels. Vertical asymptote is at x equals -1 since it didn't cancel. Now I'm ready for the horizontal asymptote, which we did see. As I take a look at that horizontal asymptote, I only care about my lead terms, 2x squared, x squared. So y acts like 2x squared over x squared. These have the same degree, so it starts to act like the number 2. So my horizontal asymptote is y equals 2, and that's because my degrees are equal. I can go ahead and avoid long division. Let's make sure we're right. Remember, this is end behavior. So if I put in some really large numbers like 100, okay, 1.8, not super close, f of 10,000, now I'm getting closer to 2, f of, just put a bunch of zeros, I don't know what that is, but see how I'm getting closer and closer to 2. And you can check that on the other side as well. Now that we're feeling good about that, let's just type this in as a boundary. I'm going to go ahead and click on my settings and make this dashed. Done. We already had the intercepts. -14 and 7. You can do the work, and I'm going to, but if you don't have to, if you already have your intercepts and you can read them from Desmos, why not just read them, right? So for the y-intercept, we'll do the x-intercept first. We want y to be 0. And I'm going to choose my factored and simplified form. So we want y to be equal to 0. So this is going to be 0 equals 2. 0 equals 2 x minus 7 over x plus 1. If I cross multiply, I lose the x plus 1. 0 equals 2 times x minus 7. Divide by 2. I'm doing a whole bunch of work here. And I get 0 equals x minus 7. 7 equals x, which we already knew, right? So again, you don't need to do all this work. X equals 7, which is the point 7 comma 0. Y-intercept, we already had that one as well. I think it was -14. To get this one, we want to let x equals 0. We can also use this factored form here. So we're just going to put 0 and y equals 2 times 0 minus 7 over 0 plus 1, and that's -14. 0 for x, -14 for y. Okay, so that's number 2. Number 5, let's find all of the properties of this one. So for this one, we can factor it. So let's go ahead and put it in factored form. That's going to be really helpful in terms of doing the domain. We'll start with that denominator. So we've got a 2x times x. Then we need a 3 on the end. Definitely we want the 3 here, plus, and then plus 1. For my numerator, I've got -7. So if I factor my numerator, 2x and x, I need a +3 on the end. So I want both of these to be minus. Okay, so I can factor it, but nothing cancels. That means that the zeros that I get from the denominator are all vertical asymptotes. So I get a -3 here. For this one, you can just do a tiny bit of math. 2x plus 1 equals 0. 2x equals -1, and x is -1/2. Okay, so these are my domain restrictions, really not equals. If I'm doing them for my domain restrictions, there are none. Vertical asymptotes, I have x equals -1/2, x equals 3. My domain, -infinity to -1/2, parentheses, -1/2 to 3. Oh, -3. Oh, that should be a -3, shouldn't it? Did you guys catch that? Negative. Let me do this one again. -3 comes first. Okay, -3. So this should be -infinity to -3 comes first. There we go. -3, union, -3, then -1/2. Union, -1/2 to infinity. Okay. Horizontal asymptote. For the horizontal asymptote, I'm going to look at those lead terms, and they do happen to have, yay, because it's the easiest one, the same degree. Because they have the same degree, I can just go ahead and look at the first terms. It acts like 2x squared over 2x squared. I can cancel each of these, and it approaches 1. So that horizontal asymptote, no slant, is at y equals 1. X-intercept and Y-intercept. For the X-intercept, we're going to let y equal 0. So 0 equals I'm going to end up cross multiplying by my denominator. So I'm just going to set 0 equal to the numerator. 2x minus 1, x minus 3. There are two x-intercepts then, one at 3, and this is going to be positive 1/2. So my x-intercepts are 1/2 comma 0 and 3 comma 0. And then finally the y-intercept, which I think is the easiest one. I'm just going to let x equal 0. So y is equal to, let's put it into this one, because all of these terms are going to be zeros except the 3's. So when I put that in, I get 0 plus 0 plus 3 over 0 plus 0 plus 3. And this turns out to be 1. So my y-intercept is at 1, 0, comma 1. We can verify this, of course, with Desmos. So it'd be a great idea to go in and verify all of that with Desmos. Okay, this is almost our last one. So for this one, last one of this group anyway. So for this one, I do want to start by factoring. Let's do blue. So I'm going to go ahead and start this with factoring. So f of x is equal to, there's nothing to factor in the denominator, negative 3x plus 2. Let's put the numerator together. So we've got 21x, so that'd be like a 3 times 7, 3x, 7x, and then we want an 8 in the middle, and we've got a 3 on the end. I don't know that this one actually factors, because if I put a 3 here, we end up with 3 times 3, which is 9. That doesn't work. And if I put the 3 here, then we end up with 21, and that doesn't work. Okay, that's actually really good news. That makes my life easy for this part. You'll see here in a second. Okay, so let's erase that guy too. So I'm just going to go ahead and just use this one. So 21, it does not factor, x squared minus 8x plus 3. So that means that nothing cancels. This is going to give me a whole. Negative 3x plus 2 can't be 0. Negative 3x can't be negative 2. So x cannot be negative 2/3. And this is going to be a vertical asymptote. So negative infinity to negative 2/3 union negative 2/3 to infinity. Just taking that number line and skipping over negative 2/3. Wholes, there are none. Nothing cancels. Vertical asymptote, x equals negative 2/3. Horizontal asymptote. I need to compare first terms with first terms. My numerator's degree is bigger than my denominator. So numerator is bigger than my denominator. This means I have a slant asymptote, and I need to go ahead and do long division. So negative 3x plus 2 into 21x squared minus 8x plus 3. Okay, here we go. Negative 3x goes into 21x squared. I need a negative 7x, right? So negative 7x, multiply it through 21x squared, and this is going to be minus 14x. Subtract, so I change my signs. 14 minus 8 is 6, so 6x, and then bring down the 3. To go from negative 3 to 6x, I need a negative 2. And I don't need to go any further because I'm already here at my quotient. Anything else is going to be a remainder. So this is what y is approaching. There's not a horizontal asymptote. Instead, it's slant. Can only be one or the other. And we say that y is equal to the quotient, negative 7x minus 2. Okay, x-intercept. We find that by letting y equal 0. So 0 is equal to my original function, 21x squared minus 8x plus 3. And then in the denominator, it was 3x minus 2. Let's see if I remembered that right. Yep, negative 3x plus 2. So close. I'm going to cross multiply, which means I lose this. So I end up with 0 equals 21x squared minus 8x plus 3. I need to find myself two x-intercepts. I'm going to need the quadratic formula here. A is 21, B is negative 8, C is 3. So x equals the opposite of b, which is 8, plus or minus the square root of b squared, 64, minus 4 times 21 times 3, huge, divided by 2 times a, 2 times 21. Let me go ahead and grab my calculator. So 64 minus 4 times, where we go? Okay, 4 times 21 times 3. That gives me a negative inside my square root, which, believe it or not, is actually really good news because I end up with 8 plus or minus the square root of negative 188. 188 all over 42. This is imaginary. This is not an element of the real number. So that's not a real number, which means that there are none. So if you end up doing the quadratic formula and you get a negative inside your root, that means that there are complex but not real zeros, so no x-intercepts. For the y-intercept, I'm going to let all of my x's equal 0. So as I put that in here, using my function here, y is equal to 0 minus 0 plus 3 over 0 plus 2. So I end up with 3 over 2. So y is 3 over 2 as a point, 0, 3 halves. It's a really good one to verify with Desmos. I'm going to do it, and I strongly encourage you to do it as well. I really would probably even start with Desmos. Let's see. So let's just change this last one. So 21, and then I've got minus 8x plus 3. And then in the denominator, oh, really close, negative 3x plus 2. Negative. We shouldn't see any x-intercepts, and there are no x-intercepts. If I zoom out a little bit, I can see that I have a vertical asymptote, and it looks like that slant asymptote. Where was that slant asymptote? Let's put it in there. The slant asymptote was negative 7x minus 2. Y equals negative 7x minus 2. I'm going to change that color. I do not want the same color. We'll make it orange, and we'll make it dotted. And then let's take a look. Okay, no x-intercepts is looking really good. And I see that really nice asymptotic behavior with my slant asymptote. Okay, excellent. So I'm feeling really good about that answer. Okay, so now we've got just a couple more, just a couple more examples. We want to put these together. Whoops, let me make this larger. Not going to use Desmos anymore. We go back to that one. Okay, so we want to create a rational function in factored form with the following properties. It's actually easier to go backwards. I have vertical asymptotes of a 3 and a negative 4. So this is f of x equals. So that means I have factors that give me those as zeros that don't cancel. Okay, so far so good. So check, check. An x-intercept of negative 1, that comes from the numerator. So this is going to be an x plus 1 and 5, x minus 5. Let me put those in yellow. These come from my x-intercepts. And a y-intercept of 0, 6. The y-intercept is going to help me check this to see if there's any kind of a multiplier a out in front. So let's go ahead and put in 0 for x and check for a. So for this one, we're going to plug it in and find a. Okay, so as we plug this in, f of x or y is 6, 6 equals a, x is 0, 0 plus 1, 0 minus 5 over 0 minus 3, 0 plus 4. So 6 is equal to, this is going to be negative 5 over 12. So it's going to be positive 5/12 a. Cross multiply, so I get 12 over 5 times 6 equals a. Nothing to simplify, 72/5 equals a. So out in front, instead of that a, we want a 72/5. I would never have guessed that. So to finish this off, I'll put this in blue. We can write this as a 72 in the numerator and a 5 in the denominator. That's one worth checking. So let's go ahead and put this one into Desmos and make sure we get the properties that we were expecting. So f of x equals 72, parentheses, x plus 1. These are the zeros, x minus 5. In the denominator, we have 5, x minus 3, x plus 4. Okay, so let's check f of 0. And f of 0 equals 6, so that makes me super happy. We also have x-intercepts of -1, so let's try f of -1. It should be 0, excellent, and 5. f of 5 should also be 0. So I'm feeling really, really good about my function, and you could do even more with it if you wanted, just to make sure that you had the right look. Okay, so there's that first function. Okay, let's do the next one. Kind of getting the swing of it here. So for the next one, we've got vertical asymptotes. I'm going to start over here. Give myself a fraction to work with of -6 and -3. Those go in the denominator. So that'd be an x plus 6 and an x plus 3. X-intercepts, those go in the numerator of x minus 6. So this is going to be x plus 6 and x minus 3, x plus 3. And then a horizontal asymptote. You know what? Let's change this a little bit because I think that's a typo. Let's make those both positive. Otherwise, it would just all cancel. So I'm going to make these guys positive here. So in the numerator, I want x minus 6 and I want x minus 3. And we have a horizontal asymptote at y equals 10. So that means I need, this is going to be degree 2. This is actually really nice because as long as these degrees equal, and they do, the degree of my numerator equals the degree of the denominator, that 10 is just going to go right out in front there. So y equals 10 goes right in front. So our factored form is 10. With the positive x-intercepts, we have x minus 6, x minus 3, and in the denominator, x plus 6, x plus 3. And you could graph that to make sure that you have everything like you want it. Okay, last but not least. So we've got vertical asymptotes. There's 2 of them. So f of x is equal to 6, that would be minus 6, and -5, that would be x plus 5. X-intercepts go in the numerator, x plus 1, x plus 3, and a horizontal asymptote of 19. Oh, this one's also super nice. So as long as those degrees are equal, and they are, both degrees equal 2, numerator and denominator, I just want to put a 19 out here in front.